Hello, everyone, and welcome. My name is Liz Temper, and I'll be your moderator for today's WJE webinar, Movable Bridge Balance and Strain Gauge Operational Testing Explained. During the next hour, WJE mechanical engineers Ralph Giernacky and Adam Mills will explore the fundamentals of movable bridge balance for bascule and vertical lift bridges, and will highlight the benefits of strain gauge operational testing. This presentation is copyrighted by Giernacky Associates. And now I'll turn it over to Ralph to get us started. Ralph?
Thank you very much, Liz. Good afternoon, everyone. Today we have a presentation focused on the use of strain gauges to record operational loading on rotating span drive machinery to determine the balance condition of a movable span. Adam and I combined have 30 years of experience and have performed strain gauge testing on over 150 unique movable bridges. We have encountered products that have gone as planned and those that have had unexpected results. This collective experience has led us to want to share the fundamentals of strain gauge operational testing for the movable bridge industry. By the end of today's presentation, you will be able to describe the benefits of measuring the balance condition of a movable bridge using strain gauges, identify the fundamental principles of measuring shear strain to establish shaft torque, and how to take that shaft torque and process it to determine bridge balance. In addition, we will go over balance considerations for bascule and vertical lift bridges. We are going to review why movable bridge balance is important, review strain gauge fundamentals, and talk about how that strain gauges are implemented in the field to establish bridge balance, followed up by balance considerations for bascule bridges, then vertical bridges, and then at the end review the benefits of performing strain gauge operational testing and when it's advisable to perform that balance testing. I'd like to turn it over to Adam, who will now discuss some of the basics to get us started.
Thanks a lot, Ralph. So today we'll be primarily focusing on the balance considerations for two types of movable bridges, bascules and vertical lifts. So what is a bascule bridge? Well, bascule is the French word for scale. And the earliest scales were simply two plates on either side of a fulcrum. In fact, our English word for balance comes from the Latin word bilengs, two plates. So balance is intrinsically tied to a bascule bridge. For a bascule bridge, the fulcrum is the center of rotation, highlighted here in the photo. And instead of plates, you have the bascule bridge has a span on one side and a counterweight on the other. There are several subtypes of bascule bridges. You have your typical trunnion bascule and your fancy trunnion bascule, Dutch-style overhead counterweight, rolling lift, raw type, Strauss-style trunnion. You can start to sound like Bubba from Forrest Gump talking about all the different subtypes of bascule bridges. However, these are the most common bascule bridges you'll encounter. Now, a vertical lift bridge, as the name implies, is a movable span that raises vertically with a span attached to a counterweight via counterweight ropes. The counterweight ropes are supported by sheaves, which are shown here in this photo. There are two subtypes of vertical lift bridges, a tower drive, which, as the name implies, has the drive machinery located in the tower, and a span drive, which, as you can guess, has the drive machinery located on the movable span. Whether you're dealing with a bascule bridge or a vertical lift, a bascule bridge or a vertical lift, the balance of the bridge is an important consideration. Now, the term imbalance is commonly used interchangeably with bridge balance. Simply put, an imbalance exists when there's a difference between the weight of a span and the weight of a counterweight. It's always desirable to maintain a slightly span-heavy balance condition with a movable bridge in the seated position. This way, the bridge is stable and reliable to traffic and has a tendency to remain closed when seated. With a relatively small imbalance, a movable span requires less power to operate through the range of motion. Each movable bridge is designed and constructed to operate under a specific range of imbalance. When a bridge's balance condition is outside the design intent, a number of problems can arise, including overloading of the electrical drives, overloading of the drive machinery, unacceptable operational behavior, unacceptable stability when seated, any of which can result in damage to the structure or injury to personnel or the traveling public. Bridge balance is an essential consideration for every movable bridge owner will be responsible for maintaining safe operation of the bridge, the contractor who's responsible for modification of the movable span, as well as maintaining safe operation of the bridge, and the designer who's responsible for design capacity, which includes specifying an acceptable range of balance for the bridge to operate through. Consideration for movable bridge balance requires a multidisciplinary approach among structural, electrical, and mechanical engineering. Changes to the balance condition can result in loading outside of the intended design capacity. We were involved in a project where the balance of the movable bridge was changed to meet the requirements of the rehabilitation design. However, with the span balance altered, within the project constraints, the driver was unable to operate the span. The balance condition had to be changed to ensure safe span operation. Now, performing operational strain gauge testing can quantify your bridge balance and establish the requirements to achieve the desirable balance condition. Before we go further into performing strain gauge balance testing, we need to talk about what a strain gauge is. Before we do that, we need to define what strain is. Now, strain is essentially a ratio. It's a ratio of the elongation of a material to the initial length of that material, delta L over L. A strain gauge is essentially just a resistor. It's a sensor whose resistance changes with elongation. A voltage drop occurs due to this change in resistance, and we can measure that voltage drop to determine strain. For the purpose of balance testing, the strain gauges are wired into what's called a full Wheatstone bridge. This configuration involves wiring 4 strain gauges as shown. With this configuration, we can determine relative changes in resistance as well as measure minuscule changes in strain. Now, strain gauge testing is predicated on being able to measure torque in a shaft. And what is torque? It's simply a twisting force that causes rotation. The full Wheatstone bridge is installed onto a rotating shaft, oriented as shown, 45 degrees from the shaft axis. 2 gauges installed on either side of the shaft. The benefits of this are threefold. We can measure shear strain due to torque, and the Wheatstone bridge configuration compensates for thermal effects, compensates for bending, and compensates for axial strain. Now, what is shear strain? Shear strain is the strain that results due to a torque applied to the shaft. When the torque is applied, localized deformation occurs. And when the strain gauges are installed in the shaft, we can directly measure the strain at that location. The equation is a factor of the geometry and the material of the shaft. G being the shear modulus of the material, and J being the polar moment of inertia of the shaft. That was some of the background theory of the strain gauge implementation. Ralph is going to talk to you about more of the hands-on field implementation of strain gauges.
Thank you, Adam. Now that we've established this fundamental method of measuring shaft torque using a strain gauge, we need to record that shaft torque during operation of the movable span and plot it against the bridge position in order to calculate the span imbalance. To accomplish this, we install strain gauges on the rotating shaft in the drivetrain as shown in the photos presented here. Here, the strain gauges are spot welded to the selected drive machinery shaft. Gauges can also be bonded directly to the shaft. However, spot welding is the desired method of adhering gauges to the rotating shaft due to field conditions and durability. The gauges are installed on bare metal that has been sanded to achieve an approximately 125 microinch surface finish. The gauges are then covered with a coating of polyurethane to protect them from water, then covered with a layer of butyl for further moisture protection, then a layer of neoprene to resist impacts, followed up by a layer of foil tape to protect the installation from EMF signals, and finally the layers of duct tape as the first line of defense for damaging the wire and the gauge installation. In our experience, welded gauge installations have provided up to 10 years of service life. With the gauges installed in the Wheatstone bridge configuration that Adam previously described, the circuit is directly wired to a data acquisition system that provides an excitation voltage to the circuit and conditions the signal to record calibrated shear strain. The photo on the left depicts a strain gauge installation directly wired to the data acquisition unit with the wire wrapping around the shaft during operation. The photo on the right depicts the strain gauge installation wired to a telemetry signal that is battery powered and rotates with the shaft. Either method of signal transmission is applicable for operational testing. The wireless telemetry signal, in our experience, has been a little less reliable than the wire connection. So if your recording is absolutely critical and you can't easily afford additional operations, it may be beneficial to use a wired connection. Now, there is one caveat to that, where the shaft speed, or the shaft that you selected for instrumentation, rotates at a high enough speed that it is dangerous to unwrap and wrap wires during operation. It is highly desirable then to use wireless telemetry to transmit your signal. In addition to strain signals, a span position reference is required to establish the opening forces and closing forces to calculate span imbalance. Here you can see in the left photo a conometer installed on the turn-in shaft to provide the opening angle of the bascule leaf being tested. Conometer is simply an angular measurement device that you provide a voltage to, and you measure the output voltage, and it's correlated to the opening angle. The photo on the right is a Hall effect sensor that provides indication of shaft rotations for a system event that is correlated to the lift height of a vertical lift bridge. A Hall effect sensor provides an indication when a magnet passes by. That indication is recorded as a change in the voltage in our data acquisition system. For a vertical lift bridge, we have found that recording a system event with a Hall effect to be a reliable and efficient means of recording a vertical lift bridge lift height. There are other means that can be utilized, such as a linear potentiometer. For our data acquisition system, we currently use a system manufactured by HBM, their SOMAT EDAC Lite unit. This provides a modular system to record multiple channels of data. There are many different varieties of data acquisition systems that provide the functionality required to record data. For field operations, it is beneficial to have a robust data acquisition unit that is rugged enough to withstand the field conditions and versatile enough to view data real time and enable data to be processed efficiently. The photo on the right is monitoring strain and span position as the testing is being conducted for immediate indication of the operational loading that the machinery is seeing. We have provided complete standalone data acquisition systems similar to what you see here to bridge owners for their own use to measure span imbalance. Proprietary SOMAT data acquisition software test control environment is used to configure each recorded channel and is set to record at 50 Hertz. Note that this frequency is less than some of the other specified recording frequencies out there. However, it has been proven that 50 Hertz is more than adequate to capture the required data for operational strain gauge testing. The data acquisition software results in a file that is then processed in Excel. So with the hardware connected to the data acquisition system, the strain gauges are ready to be referenced to a zero condition. Strain gauges are not absolute measurement devices. They require a reference point. Just as when using a scale to measure the weight of an object, the scale must be tailored to the unloaded condition. The change relative to the zero reference point is the actual shear strain the shaft is subjected to and what is recorded. For many mechanical systems, obtaining a zero torque condition is relatively straightforward, simple, and safe. The span drive machinery brakes are released and the machinery is manually rotated until there is clearance between the final gear set in the drivetrain. This could be a pinion over a rack for a bascule bridge, or a pinion that engages a ring gear attached to a sheave for a tower drive, or attached to an operating drum for a span drive vertical lift bridge. Within some drive machinery systems, there can be substantial stored energy that is released when the drive machinery brakes are released. This could be dangerous to the person releasing the brakes, and it could be result in a little bit of movement of the leaf that may cause a problem. This is specifically applicable for rail bridges. Only qualified personnel should perform this type of work. With the gauges installed, a zero obtained, and the position indicators calibrated, we are now ready to record. Both shafts and the position indicator are recorded simultaneously. The following example videos depict the recording process for a bascule leaf and then for a vertical lift bridge.
Here is the beginning of operation. Motor torque being transmitted through an enclosed gear reducer to an open gear set, to the rack pinion shaft, which transmits torque to the movable leaf. Strain gauge instrumented onto the rack pinion shaft. Signal being sent through the signal wire over to the data acquisition unit. And here you see a live readout of the strain during operation. And the angular position of the span is indicated by the kilometer attached to the trunnion. At the top middle of your screen, you see the instrumented shaft. The strain gauges are protected and wrapped in duct tape. Operation is beginning as we pan over. The Hall effect sensor is positioned to indicate shaft rotations that we use to correlate strain data to lift height, and centrally located to the machinery is our data acquisition unit that records the strain and span position during operation.
Now that we have recorded the data, we upload that data and review it in a strip chart. A strip chart presented here is comprised of strain data from each instrumented shaft and the opening angle of the leaf plotted against time. From the strip chart for this bascule bridge, you can see the leaf start to raise, the acceleration load to bring the leaf up to a steady state speed, and as the leaf continues to open, as it approaches the fully open position, it decelerates to a creep speed here, shown here, and then continues to open slowly until it reaches the full open position. Now, as the leaf starts to close, again, there is an acceleration spike to bring the operation machinery up to speed to that steady state of operation. As the leaf then lowers all the way and gets near the seated position, it also decelerates to a slower speed, and as a creep speed, it rotates the leaf slowly into the seated position. In the seated position, a load is applied in the lowering direction by the machinery. As you can see here, this is the residual seating load. Notice that the strain values decrease as the leaf opens, indicating that the leaf gets less span heavy as it opens. And during lowering, the strain values increase, indicating that the leaf gets more span heavy as it lowers. Data in the acceleration and deceleration regions of the operation are removed from the analysis to eliminate inertial loads from affecting the balance analysis. A strip chart for a vertical lift bridge is shown here and is comprised of strain data from each instrumented shaft and the lift height plotted against time. From the strip chart, again, you can see the span start to raise, the acceleration spikes required to bring the span up to a steady state speed, and then as the span continues to approach the full open position, there you can see the deceleration loads to change the operational speed to the creep speed and operate slowly to the fully open until it rises to a fully open position. As the leaf starts to lower, you can see the acceleration spikes again to bring the span up to a steady state operation. And then as it approaches the seated position, there are deceleration loads as it changes the operational speed from steady state to the creep speed until the bridge is seated. In the seated position, here you can see a small residual seating load is applied. It's a little less than the other example, but again, that's what you see here at the end of the strip chart. Again, all of these acceleration and deceleration regions are removed from the data analysis to eliminate those inertial loads. So now that we have our strain data and position of the movable bridge, how do you determine imbalance? Well, the recorded strain data is averaged to smooth out periodic fluctuations in the data and selected at uniformly increasing span position. The data is then processed to match the span position at the opening and closing at each of those selected points. The shear strain is then converted to shaft torque using the fundamental material equation shown here. Shaft torque is then multiplied by the ratio and assumed efficiencies to obtain leaf torque for bascule bridges, or for a vertical lift bridge, the counterweight shift torque or operating drum torque is then divided by the radius of the ropes to obtain the operating force. Span imbalance is calculated based on the fundamental principle that span imbalance acts in the same direction during opening and closing of the span. whereas friction always opposes the direction of motion. This results in these fundamental equations, that the opening force is equal to imbalance plus friction, the closing force is equal to imbalance minus friction. Therefore, imbalance can be calculated as the average of the opening and closing force. Friction is equal to half the difference of the forces. This analysis relies on friction being equal in both directions. Since there is no reasonable way to determine the true system friction, this assumption must be made. The data analysis presented here is for a trunnion bascule bridge. Here you can see the opening and closing leaf torques plotted against the opening angle. The data has been selected in the steady state region of the operation and the acceleration regions removed. Now the imbalance data is calculated at each distinct opening angle using the fundamental equation shown here, and that those imbalance data points follow the trend of the opening and closing torque data, as you can see. To determine the actual span imbalance, the black dashed line is fit through the calculated imbalance data points. The line that is fit through the data is based on the fundamental behavior of a rotating mass about a single point. This fundamental behavior of a rotating mass will be further explained in the next section. In addition to the imbalance curve, system friction is calculated using the equation shown and plotted here as the light blue line on this balance analysis graph. Note that the friction plot is reasonably flat, indicating that the friction value throughout operation was consistent. Now, the data analysis for a vertical lift bridge is similar, as it's based on the same fundamental equations, but it is also presented here. And you can see this is a plot of the opening and closing forces versus lift height. Again, the data has been selected in the steady state, steady speed of operation of the span, and you can see that we've removed the accelerating and decelerating regions from the data analysis, as the data does not go all the way to the vertical axis. The calculated imbalance based on the fundamental equation presented here results in the red imbalance data points plotted at each selected data incremental lift height. And again, you can see that the imbalance data follows the same trend as the operating force. The black dashed line is fit through the calculated imbalance data points. This fitted curve is governed by the fundamental imbalance equation for this lift span. The integrity of the balance analysis can be evaluated by comparing the theoretical balance curve against the actual balance data. The better the two plots overlay one another, the better the balance analysis. To establish the imbalance of the span at the seated position, the imbalance curve is extrapolated to the seated position, there the lift height of 0, and wherever it crosses that vertical axis, that defines the magnitude of imbalance with the span seated. As part of the data analysis, we also calculate the system friction using the fundamental equation presented here. It is also plotted as the blue line on this balance analysis graph. And again, note that it is reasonably flat, indicating that the friction value was reasonably consistent throughout operation. Now I will turn it over to Adam to discuss balance considerations for bascule bridges.
Thanks a lot, Ralph. Before we go into the balance considerations, let's talk about a little bit of nomenclature. So this is your bascule span, which rotates about the center of rotation. You have a span on one side, the counterweight on the other, oftentimes referred to as the toe end and the heel end. The entire weight of the span is located at a point called the center of gravity, which we call W, which is located from the center of rotation at a radial distance r. This is WR, the imbalance constant. It's located above the horizontal by some angle we call phi. We can determine the imbalance moment, which represents a moment that causes the leaf rotation due to the influence of gravity. Wx equals Wr cosine C. It's common practice, though, to equate the imbalance moment Wx to an equivalent force applied to the toe of the leaf, which is typically referred to as the toe reaction. It can be expressed as Wx divided by leaf length. So why are we using polar coordinates to locate center of gravity? Why not the Cartesian system, the simple x and y's? Well, it's because our bridge rotates. It rotates at some opening angle theta. We can track the imbalance throughout the entire operation with this equation, Wx equals Wr cosine C plus theta. This is a typical generic example of what span drive machinery may look like for a bascule bridge. At the center, you have your high-speed machinery, your brakes and your motors, applying torque through a gear reducer, outputs to a cross shaft, some open gearing supported by some bearings. Ultimately, terminates at a rack and pinion. That could be a curved rack for a trunnion bascule or a flat rack for a rolling lift or what have you. But the important thing is that you want to install your strain gauges as close to the rack pinion as possible. This will eliminate any inefficiencies that exist further down the drivetrain. Now that we have established where we're going to install our gauges and how to determine our center of gravity, where do you want your center of gravity to be located? Well, AASHTO provides the following commentary regarding bridge balance in absence of owner-provided guidelines. You have a C angle plus or minus 20 degrees, a toe reaction of 1,000 pounds per girder for a single leaf and 1,500 per girder for a double leaf. However, before an owner or an engineer specifies or changes the imbalance condition of a bridge, they should verify that the drive has a capacity that's adequate to accommodate this change in imbalance. Essentially, there's two schools of thought of where you want your center of gravity to be located. One thought of having a low center of gravity, which results in the maximum span-heavy balance condition when the bridge is fully seated. Also results at a neutral balance condition when the bridge is fully raised. The WR is essentially at 90 degrees directly above. This allows the machinery to have additional capacity to resist wind load when the bridge is in the full open position. Also results in a bridge of never counterweight heavy, which facilitates lowering the bridge closed manually in the event you lose power. The second school of thought is to have a higher center of gravity. This also results in the maximum span-heavy balance condition when the bridge is fully seated, and it results in the maximum counterweight heavy balance condition when the bridge is fully raised. Under this balance condition, the machinery sees equal loading when opening and closing. And this condition tends to, the bridge will tend to remain open when raised and remain closed when seated. Ultimately, though, it's up to the owner. There's many factors that come into play. Climate, if you have high wind loads, if you're in Florida, you want to have extra machinery capacity to resist wind loading when fully open. If you're in Chicago, you have additional heavy ice loading when fully seated. You want to have some additional machinery capacity when fully seated. Is your bridge typically left in the open position? You might want to change where your CG is located based on that. What kind of capacity can your drive handle, etc. An example of why bridge balance is important for bascule bridges occurred at a rolling lift bridge. It was built in the 1920s. And it is not supplied with a differential. The differential is a mechanical component that splits the drive load equally side to side. When there's an absence of a differential, it's really important to track side-to-side load sharing of your machinery. So during a painting contract, the operator was reporting the bridge appeared to be counterweight heavy. We showed up and performed strain gauge testing, which indicated the bridge was sufficiently span heavy. An investigation found that there's some blast material that ended up on the flat tread. So when the bridge was in a fully raised position, the operator felt additional resistance when trying to lower the bridge, which he interpreted as a counterweight heavy condition. However, strain gauge testing showed that the loading was clear that the bridge was span heavy. One of the limitations to relying on operator feel for determining imbalance is demonstrated there. This bridge also underwent a recent rehab, which involved removing much of the open gearing, rebushing the bearings, and reinstalling the gearing. At the completion of the contract, the operator noticed that the tips of the two leaves were offset. We performed strain gauge balance testing, which showed poor load sharing existed. This is a strip chart from that test. There's a few things of note I want to point out here. The first is the opposite pinion is in contact on the opening face. So the lines here in yellow are mostly positive, whereas the adjacent shaft is mostly in contact on the closing face. You have negative strain. Essentially what this means is that the two pinions on either side of the machinery are fighting the bridge. One tends to want to open the bridge and the other tends to want to close the bridge. Additionally, I want to point out the significant seating loads that were being developed and the large disparity in seating loads. Again, these are things that you can determine with strain gauge testing that aren't visible in other methods of measuring or determining bridge imbalance. Ultimately, this offset that was noted at the tip of the leaves and the poor load sharing was determined to be a result of an open gearing indexing issue. Initial testing was performed by others. However, the results did not present side-to-side load sharing. They only presented total imbalance of the bridge. This highlights the importance of owners and contractors to really understand what they are asking for when they request strain gauge testing to be performed. Strain gauge testing does provide imbalance, however, also provides a lot of information about load sharing and machinery loading in general. So those are some of the concerns and considerations for balance of a bascule bridge. I'm going to kick it over back to Ralph so he can talk about the considerations for vertical lift bridges.
Thank you very much, Adam. As we presented, a vertical lift bridge is a movable span that raises vertically with the span attached to a counterweight via counterweight ropes that are supported by a sheave, as shown in the photo here. The difference in the weight on the span side and the weight on the counterweight side of the sheave is the span imbalance. As a vertical lift bridge is raised, the initial imbalance in the seated position changes as the counterweight rope weight transfers from the span side to the counterweight side. This transfer of weight can be compensated for by the use of balance chains or an auxiliary counterweight system. There are two types of vertical lift bridges that we'll be discussing here that we've already presented: the tower drive and a span drive. Whether a tower drive or span drive vertical lift bridge, for a vehicular bridge, Astra provides commentary for a vertical lift bridge imbalance to have a downward reaction ranging from 1,000 pounds to 2,700 pounds span heavy per corner. Astra also prescribes that a vertical lift bridge have an auxiliary counterweight or balance chain system for lift heights over 80 feet to compensate for the counterweight rope weight change during operation. Now, there have been other bridges out there that have a heavier imbalance than what Astra has prescribed. Ultimately, it does come back down to the designer and owner as to what you're going to design your machinery and bridge for. ARIMA actually stays silent on determining the magnitude of imbalance in the seated position, and again, relies on the owner and the designer to come up to decide and specify what they would like. However, ARIMA does prescribe that auxiliary counterweight or balance chains be provided for lift spans greater than 40 feet. The span balance analysis of a span drive vertical lift bridge, as is the bridge that is shown here, relies on calculating the force in the operating ropes to raise and lower the span. The force is measured via strain gauges instrumented on the machinery shaft that drives the operating rope drums. The lift bridge featured here has a span drive machinery that consists of 4 independent operating rope drums. This is a representative schematic of the span drive machinery for a vertical lift bridge with 4 independent operating rope drums. And as you can see, the strain gauges are installed on the shaft that drives each operating rope drum, and so that you can measure the operating rope loads at each corner of the bridge. As opposed to this span drive machinery shown here that has a common drive pinion for a pair of operating rope drums. The strain gauges are installed in the cross shaft that connects and drives that common pinion, but you can only record the data for one side of the lift span. With this machinery configuration, the total opening and closing force for a given side can be established, but not a corner total. The end totals must be assumed to be split equally on a given side of the span, as there is no other way to distribute the load between the known distribution of the load between the pair of operating rope runs. This is another span drive vertical lift bridge where the span imbalance relies on measuring the force using operating ropes. You can see the arrows indicate the operating ropes supported along the length of the span, and they are used to apply forces to raise and lower the span. This particular span drive vertical lift bridge has no imbalance compensation, such as a balance chains or auxiliary counterweight system that we've been touching on. The fundamental balance equation for this bridge is linear, the simple equation y equals mx plus b. Here is the data analysis for that fundamental linear equation. The strip chart on the left and the balance analysis are on the right are from a tower drive vertical lift bridge without any of those compensation machinery, either auxiliary counterweights or balance. Behavior of the balance throughout operation is linear. For this particular case, the seated imbalance is 55 kips span heavy per end and negative 69 kips counterweight heavy when fully raised. This is in fact the intended balance condition for this particular structure, but is a perfect example of the linear behavior of the balance change as the lift span is operated. Now this schematic shows a tower drive vertical lift bridge that uses balance chains to compensate for the change in imbalance during operation. Balance chains are typically designed to directly and equally compensate for the change in imbalance through each foot of operation through the entire range of travel. As you can see here, the balance chain is connected from the counterweight to the tower leg. As the span raises from this balance chain weight is transferred from the counterweight to the tower to compensate for the weight of the counterweight ropes passing from the span side to the counterweight side. The resultant fundamental equation for this bridge is also linear, but because of the direct compensation of weight, has little to no slope. This is the data analysis presented for a bridge that has balance chains. You can see the strip chart recording on the left has equal or reasonably similar loading throughout the entire operation of the bridge. And you can see that the balance analysis on the right has a linear and nearly flat slope to it. Now, another form of compensation is an auxiliary counterweight system. This bridge is a tower drive vertical lift bridge with an auxiliary counterweight system. This schematic shows depicts the typical tower drive vertical lift bridge machinery. I highlight this to show where the strain gauges are placed in the span drive machinery and that we are recording this for each corner of the lift span. Note that Adam presented a desire to have the strain gauges installed on the final rack pinion shaft in the drivetrain. However, that is not available as that was enclosed within that open gearing gear set there right before the final rack pinion shaft, and the installation was inaccessible. Note that there is not a differential to equally distribute the load between the corners of the lift span, which is typical. However, what is to note is that this machinery is equipped with a means of indexing the distribution of load to one corner versus the other, and that's where we discuss load sharing. Sometimes you have to index the machinery to equally load the the forces at each corner of your bridge. This schematic depicts the details of the auxiliary counterweight system shown on the photo 2 slides ago. The auxiliary counterweight system shown applies a force on the lift span in the opening direction when the span is seated. The force decreases as the span raises. Then, as the auxiliary counterweight pivot passes over the orange horizontal line shown here, the force on the lift span changes from the opening direction to the closing direction, and it continually compensates for the balance change of the counterweight ropes for this vertical lift bridge throughout the entire range of motion. The fundamental balance equation for this auxiliary counterweight system is presented here and relies on the geometry of that auxiliary counterweight system. And the behavior of this is sinusoidal in nature, as you'll see shortly. Another schematic, just to show a different version of the auxiliary counterweight system, here relies on a similar principle as shown in the previous slide. However, the connection point is not at the lift girder. It is actually on about the quarter point of the truss for this span drive vertical lift bridge. And as that auxiliary counterweight rope passes over a horizontal line, the force being applied by the auxiliary counterweight ropes goes from in the raising direction to the lowering direction. Now, as I touched upon, the behavior of that fundamental balance equation is sinusoidal. And here you can see the strip chart for this tower drive vertical lift bridge with an auxiliary counterweight. And you can see that the behavior of the operational clearly follows a sine wave, and that is the fundamental balance equation for this specific auxiliary counterweight system. Here you can see the actual data analysis and the equation that the fundamental balance equation that this data analysis relies on to enable the fitted curve to match the imbalance data and then extrapolated to establish the seated imbalance of this particular vertical lift bridge. One case study that I want to highlight is corner load sharing. Here we have a tower drive vertical lift bridge where the loads in the north corner and south corner during opening were not equal. In other words, you can see the blue line is carrying more strain than the orange trace. Now, that could also be indicative of transverse imbalance. In other words, if you had a corner that was heavier, maybe the northeast corner is heavier than the southeast corner. However, through trial and error and in indexing the machinery, we were able to prove that what you see here was simply the fact that half of the drivetrain was indexed differently than the other half of the drivetrain. So by disengaging a clutch that connects the two halves of the drivetrain, we're able to match up the tooth contact on the closing face of the ring gear, and as you can see here, you get equal load sharing in the opening direction. This is after the machinery was indexed. And you can see that the trace in the northeast corner overlaps the southeast corner very well. Now, when there is a low load on the system, you can see that the orange and blue don't actually overlap perfectly in the lowering direction, but that is a function of, I think, the low load, what can be contributed there. But you can also see an example of good load sharing when the bridge is seated. Here you can see the orange and blue trace has nearly identical residual seating loads shown. Now I'd like to kick it back over to Adam, who's going to highlight the benefits of strain gauge operational testing.
Thanks a lot, Ralph. Typically, the primary purpose of performing strain gauge testing is to determine imbalance. As Ralph explained earlier, we can quantify system friction at the same time, and this is helpful to have historical documentation of your system friction, or to identify a problem you may be experiencing, if it's a mechanical component or structural interference. Also, strain gauge testing is a good way to quantify required weight changes that may be necessary to achieve a desirable balance condition, to meet a project spec, or to improve operational behavior, whatever your case may be. But the other benefit of strain gauge balance testing, which we have touched upon here, is to document machinery loading during operation. You can identify if overloading of your machinery or drive is occurring. You can identify any abnormal seating or drive behavior, and you can observe side-to-side load sharing. This strip chart is from a bascule bridge where we performed some testing and we diagnosed that the differential was malfunctioning. This is pretty evident by the fact that the north shaft is carrying very little load and the south shaft carrying significant load. Additionally, it's noted from the testing that significant load spikes were occurring and machinery was being overloaded during operation. Now, this is a strip chart of the same bridge after rehabilitating the differential and making modifications to the control system. You can see the large spikes and the data have been eliminated. Additionally, good load sharing is now achieved, as evidenced by the data of the north and south shafts that are essentially lying on top of each other. This demonstrates a clear benefit of strain gauge testing when you're seeing machinery loading. Again, I want to reiterate, this is the initial condition we found the bridge at and final condition of the bridge. So yeah, clear benefits for determining load, operational loads on your machinery. But you know, a lot of this discussion has been about balance. Can't we determine balance some other way and not use strain gauges? There are other methods that I've mentioned. One being operator feel, which I've talked about briefly already. It is helpful. Operator input is very helpful. They can indicate if there has been a change in the bridge behavior, or if they're having seating issues, or if they feel like the machinery is slipping through a break, etc. However, ultimately it's subjective, and each operator will have a different feel. You can also analyze the open gearing grease pattern, and that can tell you if the bridge, you know, if there's contact on the opening face all the way through the gearing, then that indicates a span-heavy balance condition. However, it does not tell you magnitude of balance. It could be 5 kips span-heavy or 50 kips span-heavy. You can perform drift testing, but this is it's impacted by friction, which may hold the bridge up, or as we discussed before, debris on a rolling flat tread, for example. And if there's a gross imbalance, it could become a dangerous situation to release brakes and allow your bridge to drift. Motor current readings also do not measure load directly in the pinion shaft like you can do with strain gauges. Ultimately, all these methods are non-quantifiable methods, and you cannot see the machinery loading in real time. So we understand the importance of it and how to do it. When do we perform it? Well, you perform it simply when required to by project specifications. You do it before and after a construction project, be it mechanical, electrical, or structural. When weight changes occur, either planned or emergency, we were aware of a situation where a car hit a bridge, hit a railing. The railing was removed from the bridge. No weight compensation was made. No balance testing was performed to determine the impact that railing had on imbalance. Another time to perform strain gauge testing is when operational changes are reported by an operator or by maintenance personnel. It should also be performed as part of routine maintenance and periodic bridge inspections. So we're almost at the finish line. In conclusion, movable bridge balance is an essential consideration to ensure safe and reliable operation. Each type of movable bridge is designed and constructed to operate with a specific range of imbalance conditions. Significant balance changes should not be made without understanding and evaluating the impacts to the operational loading of the machinery, of the bridge machinery. And strain gauge technology is a quantifiable, proven method of measuring span balance and operational loading of movable bridges. As part of significant changes to a movable span, strain gauge operational testing should be performed. When implemented on a regular basis, strain gauge testing can identify potential drive or machinery issues. And if changes to the operational behavior are noted, consideration should be given to perform strain gauge testing, strain gauge operational testing. So thank you for hanging out with us this past hour. I'm going to go back to Liz, and she'll read off some of your questions.
Yeah, thank you, Adam, and thank you, Ralph. As a reminder, please type your questions into the Q&A box and hit submit. We'll try to get to all the questions before the end of the hour, but if we don't get to your question during the call, Ralph or Adam will follow up with you afterward. Okay, let's take our first question. How much time does it take to perform a strain gauge balance test, and what is required?
But the time is somewhat dependent upon access to the physical installation of the strain gauge machinery. But a typical installation would be 1 or 2 days to install the gauges, and then 1 day required for operational testing. For operational testing, we typically take 3 bridge lifts, minimum of 3, and to demonstrate repeatability. Additional operations could be required if we have to stop traffic to zero the equipment, or if there are any other malfunctions encountered.
Okay, our next question. How was the friction calculated?
The friction was calculated. Yeah, I'm going to actually pull up the fundamental equations that we have.
Yeah, I pulled that slide up right now.
Thanks, Adam.
Yeah, so friction is half the difference between the opening and closing forces. The imbalance is the average. Friction is opening minus closing divided by 2.
All right, next question. What is the minimum strain required to get reliable data from the strain gauges?
Yeah, I guess I'll say our experience is that we have not encountered an installation where the gauges did not provide adequate strain to properly assess balance and loading.
Okay, our next question. My rolling lift doesn't behave the same as my trunnion bascule under the same imbalance. Why?
Oh, that is a good question. Generally, rolling lift bridges have very little friction, and that may be and that may be one of the fundamental reasons. Typically, there are other trunnion bascule or bridges that have rolling element bearings that support the trunnions that also have low friction. But in addition to the low friction, the rolling lift bridges relies on the fundamental rolling of the curved tread over the flat treads, and they're usually in different segments. So you may have a flat tread where you're rolling uphill, and then the next segment where you're rolling downhill, so that the behavior of a rolling lift bridge can actually feel like it's variable because it in fact is physically different as the structure is rolling back.
Okay, our next question. How do you compensate for environmental conditions like wind or ice when determining the span balance?
The gauges are not intelligent, so they don't know if the load that they're seeing is from the imbalance or if it's from wind acting on the bridge, or if you have a vertical lift bridge and there's equipment on the bridge, right? So it's important to perform testing when there is no other external loads acting on the bridge. So we perform testing under, when the bridge deck is visibly dry, when there's no wind or rain in the forecast, when there's no construction debris, construction materials on the lift span, especially when there's no ice or snow on the span. That's typically a requirement by the owner, by the designer. It's also typically called out for in our procedures for performing the strain gauge testing.
Okay, next question. Are new bascule bridges being built with strain gauges already installed in the mechanism?
That's a good question. There are no permanent installations that are coming and installed by drive machinery or the machinery providers. However, many new bridge installations require strain gauge testing, so that your testing company will provide a strain gauge installation that can last, it can be as permanent as it's taken care of. Like I said, we've had good experiences for using gauges up to and a little bit over 10 years. But as far as actual devices that are coming from, let's say, the OEM manufacturer, no, those aren't being installed. But generally, you will get, if you're buying a new bridge, and it should be included with the ability to measure the imbalance via strain gauges, as long as it's physically possible.
Okay, our next question. I'm having seating problems with my vertical lift bridge. Is that a sign of a balance problem?
Yeah, I can take that. Not necessarily. While a light imbalance condition could contribute to seating problems on a vertical lift, there are other factors involved, including ensuring that the machinery is properly indexed, ensuring that the live load supports are at the correct elevations, and ensuring that the control system is applying and maintaining sufficient seating torque in accordance to AASHTO recommendations. Strain gauge testing is the only way to positively, quantifiably establish the actual bridge balance, and that is a sustained seating torque is retained by the machinery. So AASHTO calls for the bridge machinery to drive the span into its seats and for the brakes to apply and to hold that seating torque. So stability issues could arise if the seating sequence, if the control system is not sequenced correctly.
Okay, next question. I've been told that my bascule bridge is light when closed but heavy when open. What can I do?
That's a good question, and it gets back to our discussion of the balance parameters which control leaf imbalance. We can show those, the WR and C there. I think it's this one. So we had previously discussed that the preferred location of the angular center of gravity be on the span side of the trunnion, either horizontal or at half the opening angle. In some cases, existing structures can have that the center of gravity directly above the center of rotation or directly below the center of rotation, which means you have no imbalance with the bridge seated, and then as the bridge raises, you get more and more span heavy. Calculations can be performed to determine what weight change would be required to shift that angular location of the center of gravity to have a favorable imbalance, but the ability to implement and achieve that kind of desired balance condition is limited to the physical constraints of where you can put your ballast installation or your weight installation, and where it can be added on the structure.
All right, we've got time for one more question. We're in the process of refurbishing a bascule bridge, which will include adding weight to the span via new grading. Do we need to balance test the bridge before construction in order to obtain a strain baseline?
Yeah, that's a great question. Yes, absolutely. You have a bridge that is operating reliably under the current balance condition. You would like to return the bridge back to that existing balance condition at the completion of your project. So a baseline strain gauge balance test will tell you a few things, like we've talked about. It'll tell you what the current balance is, where your CG is, et cetera. It'll show you machinery loading, make sure any work done to the bridge does not disrupt how your machinery is currently operating. And performing balance calculations is a good idea as well to understand, is the new grading significantly lighter than the old, et cetera, to understand what kind of impact your new grading will have and what kind of balance adjustments you'll need to make to your counterweight. And additionally, strain gauge testing can tell you at the end of the day exactly how much weight to install or to remove from a counterweight.
All right. Thank you, Adam, and thank you, Ralph, for the great presentation. And thank you all for joining us today. We hope it's been educational. If you have any questions about the topics covered in the presentation today, please don't hesitate to reach out to Ralph or Adam. Their contact information is on the screen. And if you have any questions about today's webinar or other WJA webinars, please reach out to me, Liz Pimper, at lpimper@wja.com. So again, thank you so much for your time, and we hope you have a great rest of the day.